Hey, welcome. Today we're going to dive into this incredible, kind of invisible principle that organizes everything from a tiny ant colony all the way up to something as massive as Wikipedia. It's this force that lets huge groups collaborate without any bosses, no managers, not even any direct conversation. So, how in the world does that work? Let's get into it.
I know, it sounds like the beginning of a really weird joke, right? But this question, it's really at the heart of what we're talking about today. On one hand, you've got this marvel of the natural world, a superorganism. On the other, a marvel of human ingenuity, a global encyclopedia built by millions. And the answer, the surprising thing that connects them, is a single, powerful idea called Stigmergy.
Okay, so let's start with the central puzzle. How do you get these incredibly complex, intelligent systems to just appear without any kind of central plan or a leader calling all the shots?
I mean, really think about that for a second. These structures have complex ventilation systems, they have fungal gardens, specific chambers, all built with mind-boggling precision by millions of tiny insects that are basically blind. There's no queen termite yelling orders, no foreman with a clipboard. How is that even possible? What's coordinating this unbelievable feat of engineering?
And here's our first major clue. The termites aren't chatting with each other. They're not holding little termite meetings. The real secret is something much more subtle, but honestly, way more powerful.
So what is this invisible blueprint? Well, this powerful mechanism, this idea of indirect collaboration, has a name. And that name is Stigmergy.
Okay, that sounds a little academic, right? So what does it actually mean? Well, put simply, Stigmergy is just communication through the environment. Instead of me telling you what to do, I just do some work and leave a trace of it behind. That trace then acts as a signal, like a little breadcrumb, for the next person to come along and know exactly what to do next.
And get this, the whole idea came directly from watching those amazing termites. Back in the 1950s, this zoologist Pierre-Paul Grasset was just totally baffled by how they coordinated. So he came up with the term to describe what he was seeing. The work itself was directing the workers.
And the name itself is just perfect. It comes from two Greek words, stigma, which means a sign or a trace, and ergon, which means action or work. So it literally translates to action inspired by signs. A simple, beautiful explanation for something so powerful.
So how does this actually play out in the real world? Well, it all boils down to this surprisingly simple and elegant little loop that just repeats over and over.
Let's use the classic example, right? An ant looking for food. The first ant, that's our agent, it wanders around, finds some food, and on its way back to the nest, it leaves behind a chemical trail of pheromones. That trail is the sign. A little later, another ant stumbles across that powerful pheromone sign, and it's immediately stimulated to follow it. And as it does, it reinforces the trail with its own pheromones. More ants follow, the signal gets stronger and stronger, and boom, you've got a super efficient ant highway leading straight to the food. And the best part? Nobody had to say a single word.
So this whole system really just breaks down into three key parts. You've got the agents, those are the doers, the workers. You've got the signs, the traces they leave behind, and then you have the environment. And this is crucial. The environment isn't just a passive backdrop here. It's the active go-between, the shared whiteboard where all the communication happens. It's the system's memory.
Now, a system this smart, this efficient, you just know it wasn't going to stay stuck in the natural world, right? Computer scientists and engineers looked at these insect colonies and had a light bulb moment, realizing they could borrow this exact idea to solve some of our own really complex problems.
And that led directly to things like ant colony optimization. These algorithms are basically a digital version of Stigmergy. They're used for all sorts of stuff, from logistics, like how does a company like Amazon figure out the absolute fastest route for all its delivery trucks, to designing telecommunication networks. You have virtual ants leaving digital pheromones to mark the best paths. It's brilliant.
And that's really the magic of it all. You don't have to design some giant, complicated top-down solution. You just create very simple rules for individual agents. Then you let thousands or even millions of them loose into a shared environment, and a really smart system-wide solution just emerges, all by itself. It's intelligence from the ground up.
All right, now this is where things get really interesting, because this ancient biological principle, it turns out it's basically the ghost in the machine of the modern internet, shaping the digital world we all live in every single day. See, as the internet grew up, as it evolved from these static, read-only pages to what we now call Web 2.0, the collaborative, user-generated web, it basically transformed into one gigantic global environment perfect for Stigmergy. Platforms like wikis, blogs, and social media weren't just about consuming content anymore. They were all about creating and changing a shared digital space.
Which of course brings us right back to our original question. Just look at this Wikipedia page. This is the digital version of the termite mound or the forest floor. This is the shared environment where millions of human agents can all come together and work.
And now, look at the edit page. When a user fixes a typo, adds a new fact, or rewrites a sentence, they are doing the exact same thing as an ant laying down a pheromone trail. They're leaving a sign, a trace, in that shared environment. And that little edit stimulates the next person who comes along to improve on it, or correct it, or add something new.
And check this out. This is the system's memory. The History tab on Wikipedia is a perfect time-stamped log of every single trace ever left behind. Nothing gets lost. This persistent collective memory is what allows the whole community to coordinate their actions across decades and continents without ever needing to talk to each other.
Okay, so let's just lay it all out, side by side, so it's crystal clear. In one column you have the ant, in the other the human contributor. Those are the agents. The sign is the pheromone trail, or the article edit. The environment is the forest floor, or the wiki page. And in both cases, you have simple individual actions guided by signs that all add up to achieve a massive emergent goal: finding food or building the world's biggest encyclopedia. It's the exact same process at work. So this all leads to a pretty mind-bending final thought. If we are all participating in these huge Stigmergic systems online every day, what is it that we're actually building together?
You know, Tim O'Reilly, who was a really central figure in thinking about Web 2.0, he kind of nailed it with this quote. He said, "We're harnessing collective intelligence, turning the web into a kind of global brain. Every link we create, every article we edit, is like a new neuron firing, a new connection being made in this huge, distributed brain that spans the entire planet."
And that leaves us with this one last, kind of profound question. A single ant has no idea what a colony is. It has no concept of the giant, complex mound it's helping to build. It's just following simple rules, reacting to signs in front of it. So, as we click and share and edit online, are we any different? Are we all just tiny agents building something so vast and complex that no single one of us can see the whole picture? It's definitely something to chew on. Thanks for watching.